Okay, we have this one software. Sini ya rupanya. Okay, we have this. Kita ambil the sequence here. Okay, kita buka this one. Okay, this is the sequence. Okay, so you just open. So this is dipanggil position ya. This is all the position. So this is kita punya base call. Okay, this one. And ini adalah kita punya nucleotide peak. So ataupun graph. So the peak should have correspond to G here, this position here. So yang apa ni, yang merah ni dengan T, adenosine, hijau is dengan A. So you can look at all of your, so you have to look semua sekali up until the end of your sequence to look for any ambiguities. Okay. So yang ini nampak is very good. Nampak very penuh. Ini dia nampak G. This is something that the noise, okay, background on the nucleotide peak G, but the peak G is the one that have the highest peak. So that's why they call it P here, the corresponding peak. Okay, if you look macam A ni, dia tak nampak kat background it's very sharp. So there you have a very macam the concentration of A at that position is very good. Macam ini dia very weak kan. Okay, pasti yang weak ni you kena tengok lah the weak ni, meaning that the laser actually they are not 100% sure that this is A. So you have to check. So you kena check. You nampak dia ada merah belakang bawah, apa dia, cytosine, yang biru ni purple, but dia punya base call adalah A. So okay, so the A here and A, the dua sini. Okay, A and A. Okay, and etc. So you kena check. Okay, kena check. But overall the sequence is quite good because you have a very low background noise lah. Dia tak lama sangat. Sampai habis, okay, you tengok sampai habis all this. I'm not sure how many base pair. You akan nampak they try to have a gradual signal loss so this is only about 400 base pair. Okay, for the sequence. So lepas tu baru you convert, save, export export kepada FASTA format. So letak nama kata sequence A. Okay, satu save. Okay, then how do you look at dia punya apa ni, dia punya mana saya punya dia punya apa nama ni, sequence tadi this one. Okay, we go for the software tadi mana tadi, semester 2 zoology. Sorry, software this one. Sorry, this one. Coba tadi software sequence. Okay, let me just save again tak nampak. So export pada sequence dalam software STH. Okay, sudah. So dia letak dalam bentuk FASTA sequence. Ni dah ada sequence mana ni FASTA ni. Saya tak nampak dia mana saya cari dia. Save. Now how do you look at the FASTA tadi tu? Sequence 1. Tak nampak sini. Betul ke survey? Kita tak boleh save as lah. Dia kasi sequence, you have to save, you have to export. Okay, export dalam bentuk FASTA. Mana dia punya, dia ni dalam mana? Dalam semester 2. Okay, salah, saya punya salah, semester 2. Betul dah. Dapat tak saya transfer dia punya ni? software, STS, semester 2, zoology. So you have this one, software, sequence. Tak nampak dia punya ni. Okay, never mind. Yeah, this one. Okay, so this is how you convert. So kalau nak tengok dia punya apa nama ni, dia punya let's say yang the FASTA format, that's fine. This is FASTA format. Kita tengok dalam message kepada dia. So ini dia punya sequence lah. So dia akan yang more than is actually an instruction. That this is the beginning of your data set. This is dia punya this is yang the ID they given with the API format tadi. This is the punya running number. This is the punya species name. Salonis. This is apa, telur Silonia Medas one. This is the punya apa nama ni, the gene TCR5 dan sebagainya. Dia punya gene marker. So this is dia punya sequence. So in terms of having the chromatograph, they give you dia punya bentuk dalam ACTG. So this is one sample, two sample sampai dah habis. So everything this is dipanggil master file. Okay. Atau bagi my sequence. And so this is the punya yang API file, atau panggil chromato file. Okay. Now go back to our lecture just now. Ini pun ini salah. So you repeat your sequence, your samples until you finish. Export the sequence into a FASTA format. Then you create one master file. Sini kita pakai A, contohnya file a.txt, ataupun my sequence just now. All of your sequence that all the sequence that you're going to study put into one file. Okay. Baru you pergi kepada cluster X. So cluster X ni adalah alignment software. Kalau kita pergi tadi pada sequence tadi, you go to software here. It is a cluster X. Okay. So dia punya application is yang ada X ni. So you keluarkan. So you load your sequence. Ini dah buat tadi tu. Okay. So let's say kita buat sini. Saya ambil yang this one lah, numerators lah. Yang dah di apa nama text tadi. So it has to be the text document. Okay. You open. So you have this one. Okay. So this is your sample or your sequence sample with the outgroup. So let's say this is on the population study. So you have the foreigners from different population, and you have your punya outgroup ataupun the common descent lah, Kula and Eritrea here, which is closely related. Maybe in the same, Kula is in the same family, Dicloclosidae, Eritrea in the same Anura, frogs itself. Okay. Ranite, which is in the order of Anura. Okay, so we want to look at the substitution ataupun the transformation, okay, from the ancestor to the in-groups here. Okay, so this is before the alignment. So this is your data set. Okay, so the first one you dah buat, which is put check your sequence by eye in chromas, and then you put into a notepad to prepare for the subsequent analysis. Okay. So you kena buat load sequence in the text file yang dalam notepad. Kalau you pakai dalam Word, mana tak dibaca. Dia can only read from the notepad. Kalau dalam Apple, dia boleh baca dalam what they call it, dia boleh baca dalam text edit, okay, ataupun Word edit atau Wordpad. Kalau dia say computer Apple is text edit. So once you have done this, then you do the complete alignment. So you akan align. Okay. So you can nampak sini the sequences so they shows a pair of sequence 13, 14 sampai habis. Lepas dia panggil multiple complete alignment. So you can nampak sini, this is all you punya. This is conserve site, tak ada perubahan. Yang tak ada star ni adalah yang ada variable. So di sini semua C except for the outgroup dari T and A. Di sini semua sama, semua tak ada. Okay. So this one, okay, this one you can nampak at this position dia ada T, C and T. Okay. So this is the variable set. So you nampak all this, and this one deletion. So dia akan, the computer akan they will do the alignment for you. So let's say kalau priority, maybe they're short of sequence, so they will align so that everybody have the same of the position. So back to the deletion here. Okay, and you have to save. Okay, file, save sequences as, and then you put an access file, because access file is the file that can be used, can be read by the others. So that's sequences. Okay, and we look at our, so lepas tu you boleh keluar lah daripada cluster ni, and you look for your, saya tak sure ada ke tidak dia punya analysis ni, tapi tadi access file lah, so this is access file, you can see here. So access file, okay. So hashtag is actually is a standard standard command for the word file to instruct the computer that this is the type of the type the file type of this particular information. Kalau dash hashtag mega, so it's a mega format file. Kalau nexus, it's a nexus file. So nexus file, so hashtag nexus. And you insert of this begin data, which is have a dimension. I mean bilangan TXI is about 21, so ada 21 here. Okay, character ada 46 character adalah dia punya ACTG. Okay, 478 base pair. Missing format semua dia akan ambil kira simbol ABCTG and interleave data type DNA. So interleave data type DNA, this is very important for you to understand about the types of DNA data type. Dia ada dua sebenarnya yang common, which is on the interleave data type ataupun sequential. Interleave macam ni lah, you have 1 sampai let's say 80 base pair, and then you continue on the next sample sampai habis 80, sampai habis all the sample, and you go for 81 to 160 for example lah. You continue sampai you habis all those base pair of 4, 7, 8, and then you insert there is a end of the data set. So this is a DNA interleave data type. Maksudnya dia ada intermediate, ada interruption here dalam the position. It's up to you how do you going to display your data sets. Maka dalam 1 ke 100 position, 101 to 200 ataupun 1 to 80, 1 to 60. But this is what interaction of the continuous data. So 1 to 80, and then you go for the next sample sampai habis. And then 81 to 160 and go on and go on. So this is what I call the interleave data set. After that, lepas tu kita buat apa? Okay, so once we have done, so this is cluster S, ni sama lah kita dah buat tadi. Okay, and so once kita dah buat tadi, access file kita save, saya dah jawab apa ni, then kita akan go for the mega. Now before we go to the mega, let's just do some reflection here. So this is a sample example of species EXO, SJGG and Shiny with the position here 5 sampai 25. This is your nucleotides. Okay. Now how many variable sites are there in the sequence alignment above? So how do you know there is a variable? Macam sama juga you buat tengok dalam cluster X where you have a position that is not in the same nucleotide. So contoh variable adalah ini. Ini semua sama, you know. At this position 4 or 5. Every sample have K9 at the position 5, but at the position 8 here, EXO have adenosine, but the rest have thymine. Okay, so there's a variable set here. So you remember your character adalah your nucleotides, but your character state, your character adalah the position, your character state adalah the transformation of or the substitution of your nucleotides. Itu character state, macam dia berubah daripada from the A ke T ataupun T ke A. You don't know because you don't know which one is the ancestor here. Unless this is something else, let's say Liporanus and coli. So coli should be the outgroup, the ancestor. So that means from T kepada A. Okay. So this is how you kira. So from the example above, how many variable sites that you can think of? Boleh kira? How many? Termasuk deletion. This is deletion lah. Considered as variable because at the position, the rest have cytosine, but the SJ on doesn't have any nucleotides. It's a deletion on its side. So how many variable sites? Variable site is the nucleotides are what do you call it? The types of nucleotides is different from that particular position. Okay, dia tak ambil at this stage, they do not take into account the sama ada is a transition or transition, but it's a variable size. That means the perbezaan position, perbezaan yang kertas in that particular position. So how many variable site here? Class, how many variable site?
4 or 5.
4, 5. Kira.
7.
Yes, 7 lah. So 1, 2, 3, 4, 5. Lagi? 6, 7. Okay. Now, what type of DNA substitution mutation shown in the site 8? 1, 2, 3, 5, 6, 7, 8. And site 13. Here. Okay, site 8 apa? Transition or conversion?
Transversion.
Okay, conversion because it's pouring to primary DNA. What about the position 13? 13.
Transition.
Yes. Transition, good. So, how semua faham macam what is transition conversion? This is very basic genetic. Now, what class of mutation is shown in 24 here?
Deletion.
Yes, deletion. Okay, good. Now we go for the mega. Mega, you you boleh baca sendiri lah mega. This is the history of mega. Bila dia start implement 1990s. Masa saya dekat US pun saya say 1996. So at that time it was in the version 0.96. So the lots of things has been upgraded in the software. But it's very good software to explore, discover and analyze DNA and protein sequence from an evolutionary perspective. Okay. So you have Mega 4, Mega 3, and etc. Now you have Mega 10. Now before kita start doing Mega, you can also check your sequence. Meaning to say that you have to check your sequence whether they are good. Walaupun you dah check by eye. So this Mega also a software that can use to check your sequence. Especially when you do a protein coding genes, you have to translate your sequence into a protein coding gene so that you boleh check you punya subcodons. Bila you have a partial sequence, the tendency to have a stop codon is very high. So mungkin dalam one sample you have a stop codon, okay? Then you have to remove the stop codon. Now remember, untuk sequence you tak boleh remove suka-suka hati because the position is your characters. Is the one that you look at the variable. So kalau you, let's say you ada 10 sampel, one sample you have one stop codon in the middle, so you nak buang. Stop codon is sama ada apa UUA or AAG or something like that. Saya tak ingat dia punya nucleotide semua tu. But you buang, you tak boleh buang on that sample saja. You have to buang that position for the whole of the punya sample. Kalau ada 10 sample, 10 sample you kena buang at that particular position. So that everybody will be harmonious. Kalau tidak, dia tak akan jadi harmonious. You have to redo and everything. So how do we do that is by looking at the mega. Now let's look. Nanti saya check saya punya mega ada ke tidak. Do I have mega here? Mega. Yes, you have mega X. Mega 10 saya. So I have already mega 10. So kita buka mega 10 kita. Kita stop dulu ni. Atau stop ni. Jadi mega tadi tak nampak dah mega semua. Mega. HIJKM. Okay. Okay, ni mega. So this is mega 10. This is the latest lah. So you can see here the align data. So this is the data set our alignment model evolution, distance, how to kira diversity of the kertas, phylogeny, ancestral state, selection dan sebagainya. Ini saya tak explore sangat lah. Diagnosis is for the diseases dan sebagainya. Clock, dia pun boleh kira clock. Now we go, you open your, suppose you open your session dulu. Okay. Dan kita nak check kita punya sequence dulu. So bila nak buka ni, you have to convert you punya access file kepada mega. Sebab dia tak boleh baca. Jadi semester 2 zoology kita guna ni lah. Kita punya ni software dia. Sorry. Okay, we have the nasal file. Jadi and you open. Okay. Would like to view? Yes. So kita akan view. So now this is you punya Texas file tadi. So you have to use click on utilities, convert to mega format because the mega can analyze data with the with the mega format. So dia kata data file to convert, yes, you punya Nexus file, and then you convert kepada this format is a Nexus Nexus file, and okay, and you kena save. Okay, file conversion complete. So this is your mega format. So you nampak hashtag mega. So hashtag is just not for Twitter punya all those things, but it's also an instruction to the data that this is a mega format. Hashtag mega, and this is the punya apa nama ni information in this particular file. So you can see data type, nucleotide, identical missing semua, and you can say that this is what we call the sequential sequential SEQUENTIL sequential data type of DNA, sequential DNA data type, which can be reflect by the continuous on the sample of your nucleotide sampai habis. Maksudnya this is one sample of liporinase, all of this adalah the new sequence, and baru dia pergi to the next sample. This is in contrast with the interleaf data set. You have 1 to 80 for the whole sample, and then once you finish that one, then you continue for the next position 81 to 160 for the whole sample. That is interleaf. But this one is sequential because you have your data set, the complete of your nucleotide, okay, for the sample. Baru you pergi to the next sample. Kenapa saya tekankan this data type? So when you there are a lot of available software in the market, or you can get a free software, etc. And when you try to use that software, okay, so they always ask for the input file. So dia kata kalau I want a sequential data type, so you remember sequential is like what the mega have. So dia kata interleaf data type, so you know they want a nexus kind of data type. So this is a very basic information that you need to know. So kita dah ada mega, dan kita close. So baru dah kita buka. So open a file session tadi. You go for the mega format here, okay, and open. So you have here. Now, so you tengok pada sequence. So this is your sequence tadi. Okay. Sequence. Before kita tengok pada this one, there are certain things. Kita tengok alignments. So kita tengok alignment because this cytochrome oxidase. So it's a protein coding. You have to make sure that there are no stop codon in the middle of the sequence. So you have to go edit alignment, okay. Mana dia punya, okay, open a save alignment session, okay, create new alignment, retrieve a sequence from a file, okay, and you pergi kepada software tadi, sekejap pada sini, sorry, software, kenapa dia tak ada sini sekejap, macam mana saya buka semalam? So you go to align, edit. Sepatutnya you have to do sequence. Kenapa dia tak ada sini? All file. Okay, this one. Align file. This is file. Ingat saya. Let's go for mega format. Oh, dia nak tengok Nexus file. Saya pun lupa. Nexus file. This one. Kau dah boleh open. Kenapa tak boleh open? Hold on. Open a save. Saya tak pernah nampak lagi ni benda ni. Okay. Kita cuba ni. put it ada TND file. So apa yang nampak sini adalah maybe this one, this alignment. Tak boleh, kita tak boleh buka. Semalam tu boleh buka. I don't know what file yang saya guna semalam. So you can buka. So you can look at the, dia akan keluar macam cluster lah dia. Dia akan keluar macam, oh saya tak save alignment tadi untuk cluster. Okay, contoh saya tengok sini cluster punya ni. Tak ada. Ada kena buka sekejap kena buka mega format. Okay, never mind. Kita go to data. Let's say you but my sample already already clean because we already move all the all the subquadrant. Okay, before you do the analysis. Okay, so once you have you sure that there is no stop quadrant. Kalau you buat ribosomal tak ada masalah, but kalau you buat protein coding you have to check for the stop quadrant. Okay, kalau stop quadrant you have to remove everything every other position for every sample. Bukan you buat satu sampel je yang ada stop quadrant. Dia akan dalam mereka dia akan tunjuk ada stop quadrant is by the asterisk. Itu maksudnya the position dia tak boleh nak convert kepada kepada protein. Because it's a stop codon. Stop codon is symbol as asterisk. So you have to remove that position. Okay. Sometimes Mega boleh buat remove the whole thing. They will remove the tree, nucleotides, and you save that one for your further analysis. But sometimes dia tak boleh buat. Bila you tak boleh buat, you have to go back to your notepad, the text file, and you remove that position, and you do the alignment again. So memang dia akan tedious. So this is the preparation of file is quite tedious. So that you get the correct the correct sequence for the analysis. Now once you have done that, then you go for the data explorer. So this is the first thing yang kita buat. Kalau you tengok dari segi mana kita punya ni punya data analysis tadi tu. So this one, okay, this one. Okay. So kalau you tengok this one ini dia punya mega ni. This is the mega that I tell you. You open. Oh, dia nak yang alignment tadi, ALN. So I forgot to save on the alignment. Okay. So this is the alignment file and dia akan keluar macam ni. So this is sebagai dipanggil asterisk tadi yang dia akan cari. Of course this one is already being removed lah, kita tak nampak lah. But sometimes dia ada, bukan yang ini, this is for the variable set. Ini apa ni? Oh, this alignment. Okay, sorry. See the conversion. Okay, dia tak tunjuk sini. But after you finish all those sequence, so this is the data explorer. Apa yang kita buat adalah we want to look at the variable size. Conserve yang tak ada variable lah. Very conserve, there is no changes. Variable size. Variable size can be anything. Sama ada dia silent or tidak, maksudnya whether it we did to the phenotype difference atau tidak. Okay, sometimes mutation give you a silent. That means they didn't change the protein. Okay, so the one is so variable size we include of those changes. But parsimony size adalah those yang site yang that give you a signal for parsimony. Parsimony is the what you call derivation, the derive. Okay, kalau you tengok dia punya if you look at the phylogenetic terminology, is a derived characters. The changes. So derive maksud derive from the common ancestor. So only the specific will give you the information. So the more you get the parsimony, the data, the more you can get the good result. Okay, this is why the importance of having this information, because you want to indicate the marker that you use, the target gene is it a good marker or not, to infer this particular relationship. For the data set example here, we look at the population level. So when you have 74 out of 4, which is quite okay, because they have enough signal. This is panggil signal on the common descent, which is the parsimony, to indicate the relationship. So kalau dia hanya ada 1 atau 2, that means you have to redo the target gene. You have to choose another target gene, because some of the genes, let's say, is very highly variable for frogs but very conserved for birds. So that's why you have to play around with the target genes of your interest, so that you can give enough relationship to be solved. Kalau tak boleh solve, that means very low parsimony signal, that means you have to choose another gene, ataupun you have to add up the sample size. Instead of 400, you have to add up maybe 3,000 bases, so that there will be a variance or variation to infer the phylogeny. Okay, so this is important that you have to look at the variable side. Okay, so this is dia punya dalam software tu. Let's look at the software. So you go to the data sets. So ini conserve site. So dia okay, give you the highlight 331 to 478. Okay, the variable size is 147. Parsimony site is adalah 74. And singleton is mutation. Okay, dulu dia boleh 04 to 444, but this is singleton segregating sites that give you the the phenotype. Dia lebih kurang sama dengan parsimony, mungkin beza 1 or 2. So because singleton mutation, they give you a phenotypic variation. Some mutation doesn't give you any changes of the protein, but the singleton is the one that give you the change of the protein. So dia boleh kira dalam software ni 74. So when you have this kind of data set, the enough variation, so you can conclude that the CO1 is a good marker to infer the species relationship, because we're looking at the one species, not species, population relationship of one particular species. Okay, so that is why. So dari situ, kalau you punya sampel tak banyak beza, only 1 or 2 je dia punya 1 out of 478 is a singleton site, that means you cannot construct the tree, it will collapse. There is no variation to be constructed, so you have to redo, choose another gene of interest that can give you the results. Okay, enough result, that means enough variation to enough parsimony signal. Okay, to construct the relationship. So after you have done this, okay, so kita go back to kita punya tadi tu. Then we go to so this is all the verbal side, finger side dan sebagainya. Okay, and then we go for the okay, this is you punya exploring suka, write the data file. So ini saya lupa nak tunjuk tadi once kita finish, okay, once kita finish tadi this one, okay, so you have to write your data display. Sebab saya dulu guna mega lama, so sometimes this is quite new for me. Highlight statistic, percent, display result in the spreadsheet. Terpekan dari situ kita write data file. Also export data. Okay, how to write a data file from this one? Saya pun tak sure. This is a mega 10. This like data file is like yang saya tunjuk tadi, because this is very important. Sometimes you cannot you can actually detect those yang apa tambah lagi, but you can detect those yang tahu pasal phylogen molecular or those yang tidak tahu if you look at how they write the data set. Alignment, sebab what we want when you publish as a thesis or as a journal, we want a data alignment data set. Kadang dia buat macam ni lah, dia ambil ini and dia print screen. So when you have a print screen, you tak boleh nak tengok. You hanya boleh tengok when you have dia punya macam Excel lah, you boleh nampak dia punya the variable set tu. Tapi I'm not sure dekat mana for the new punya ni, how do you write the data file? Let me just this is your TA, okay. Ini tanpa alignment statistics highlight, okay, group search, display, save. Kalau kita buat export data ni macam mana? Yes, this one. So export data, ini saya jemput, saya tak adjust mana. So this is interleaf output, that means you ada ni, katalah kita tak nak interleaf, kita nak okay, we don't want the interleaf. Okay, kita nak interleaf. Just never mind. Data block, writing set numbers, yes, for each set atau at the end of the line. Okay. And then you click OK. Let's say okay, let's say kita letak OK. Dan kita save. Saya tak sure ini boleh nampak ke tidak. Kita tak nak mega format kan, cancel. So we want to use export the data set. Dalam bentuk FASTA, dalam bentuk let me see dalam bentuk, saya rasa dalam bentuk Nexus lah. Nexus. So you nampak sini ya. So ini yang you akan ambil. This is all you ambil dalam textbook. So this is will be your alignment sequence alignment. So this one. So you nampak position dia. Ini 400, 300. So you click copy and you put dalam dia punya Microsoft Word. Mana sebenarnya Microsoft Word saya? Microsoft Word. Microsoft Word. Saya punya Microsoft Word. Word. Apa? But this is the thing that kita akan. If you look at the data, so you can see dia punya variable set. Here, variable set here. You can see here variable. And this one is a outgroup. So it's this is an understand a situation. Okay, it's common situation where you have more of the variables with the outgroups. Okay, so you don't. So bila you review, you can look at dia punya alignment here. So this is then this one you just copy and put in your manuscript. Dia akan tunjuk you punya sequence. But if you just put a print screen, you cannot see dia punya ni all this, you cannot see dia punya position and etc. So dari situ you boleh tahu that the student is not really understand apa the morphology because they only give you the print. Macam ni you print screen you show dalam the manuscript. We don't want this. We want that particular alignment. Ini put alignment, but this is in the print screen. We want in the text file. Jadi dalam access file or mega format. Okay. Now after that kita buat distance kita dah. Memang main saya punya lab tak ada dah. Tak masalah apa pun tak ada masalah. Now we used to use compute pairwise distance. This is another analysis that you have to do. Pairwise distance. Yes. Kita guna and you ada banyak sini. Various method. You nak proceed atau tidak. Ini kita tak pernah buat lah. So you have, now macam mana kita nak tahu distance is before you start the distance, you have to make sure that what is the model of evolution that you have. Okay, so that data yang guna tu adalah data yang fit dia punya the rate of evolution in the sample. Sometimes kita selalu buat dulu we always use a Kimura 2 parameter because Kimura will assume that transition and transition adalah tidak sama. Okay, kalau you guna uncorrected maksudnya you tak correct pun dia punya this is very, very important to correct because every sample they have a different rates of evolution. Okay, so you have to make sure that you must get the best fit model that suit your data, because as a statistic, the less variance you have, the more it's represent the original classification. Okay, so this why you ambil those and very minimal variation that you the model that you choose have the very minimal value that represent your best fit data. So you kena buat ini before you buat the sequence, the distance, before you buat the phylogeny. So you go to this one, find best, okay, DNA module, yes, and dia akan tengok you punya ni, use all side, and you just buat okay. Kau jangan nampak dia akan buat. So this is trend ni ada dia punya. So tadi saya kata berapa banyak yang dia punya model yang ada. So this is the result here. So kita ambil the list yang paling sikit dia punya BIC or AIC ni, ACAD Information Criterion or BIC ni, that is the best fit model. Okay, so di sini bukan dia ada have more 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18 19 20 model embedded in MegaTech, which is good. Okay, more than 20. But if in the model test software itself we have 84. You have more choices, but it's okay. It's still okay because you still have 20 of you. It's quite enough. Okay, you don't have to do model test. You can use that in the Mega itself. So for this, the best fit model for our sample, for my sample is TNG93G. So this is Tamurane 93, 93. Kita ada Tamurane 2 parameter, 3 parameter G. Okay, it's the best one. As mentioned, so this one you boleh letak dalam manuscript. So the best fit model for our sample is following TN93 plus G. Gamma is the distribution model. Kenapa ini penting? Bila you buat edge of divergence, this one you have to use in your parameter later on. Okay, so once kita dah nampak dia punya result ni, so you kena buat go to, nampak masih nampak slide you go to distance, compute. Yes, dan kita guna Tamura lah, Tamurane. This one okay. Tamurane here, Tamurane model. Okay. Sama ada saya guna Tamura 3 parameter ataupun Tamura, kita guna Tamurane model lah. Sebab saya tak sure 93 tu is it maybe 2 parameter or 3 parameter. Okay. Parameter maksudnya dia ambil kira mungkin transition, ratio of transition transition, ratio of transition adalah alpha, transition adalah gamma, and other parameter adalah lain, tak sama, they are not in the same rate. So lepas tu dia panggil 3 parameter or 2 parameter. So kita ambil Tamurane model, okay, dan kita compute. So this will be your distance. So you have to look at the distance. Now the first thing you look at, you punya outgroup. So our group is 19%, 37%, which is, so the meaning that, and you look at the in groups, adalah 7.9%, 3.5, which is acceptable as it's still low divergence as compared to the outgroup. Kalau you punya sample ni 27 ataupun 18%, you know, ataupun 20% lah, okay, 20%, meaning that these in groups have more diverse than your out group. They mean that sample is wrong. You have to remove the sample, you have to redo. So the first one that you have to check is whether your sample, the in groups are actually in the right domain, so that you can proceed for the next analysis. So since they are all less than the out group, so you are still very good. Okay. So how do you prepare for the sequences? How do you write in the manuscript is you look at the within population. Look at the lowest range, the lowest value, and the highest value. That will be the range. Let's see, maybe 2.1% up to 10.9%. That is the range of the divergence for this. That means this species is highly variable because they have a very quite large, 10.9%. Okay, but if you look at the outgroup, they are still okay. Okay, itu maksud dia. And then from you can look at the within mulu saja what is the range, and within population. Mulu to develop answer. So this is you have to play around with the punya distance. This is dipanggil sequence distance. Now Lepas you dah dapat, that means you dah guna the divergence, you have a variable, so you have to construct the phylogeny. So kita dah construct, kita buat yang paling senang lah neighbor joining and you construct. So you buat bootstrap method 1000 Tamura name model and you click on. Bootstrap maksudnya you buat ada iteration sebanyak 1000 kali. You know, saya dah cerita pasal bootstrap method, you have boot and strap. You ambil sebahagian daripada data for your analysis and you tengok sebenarnya what is the relationship. Macam ni ya, that means for this barrier Brunei Mulu batang air, you buat 1000 iteration 100 kali sebab 100 ni 100% dia punya pusat barrier, 1000 time iteration dia akan keluar this kind of. Yes. Terdengar ke? Yes.
Sorry to interrupt.
Yes.
May I ask at what time lab today?
Sebelah belah. You are sekarang ni kat mana? Dekat rumah ke dekat sini?
Dekat Unimas.
Tak apalah, saya tunggulah you datang. It's okay.
Okay, doktor.
Yeah. Sebab I have to finish this soal. See all next week kita dah ada OSP. Ataupun you nak sambung next week. It's up to you. Next week kita OSP on the left side. Saya sikit lagi ya. Kita boleh beli. Tak apa, saya akan tunggu awak. Kita akan start. I will let the demo. Kita akan start lambat sikit at 11:15 ya. Which the demo. Dengan how is the lab lagi? Oh, pergi mana dulu? Is there any area yang kita jumpa before kita buat go to the desired lab? Kita ada 4 lab kan? What is the scenario? You go to the pengajaran dulu for the briefing ataupun pesyarah akan datang for every month. Guys? Hello? Okay, so this is the neighbor joining. Tak ada jawapan, so I just continue. The neighbor joining, this is by distance saja. Tengok by distance. So you can see here. So how do you interpret the tree? You nampak the outgroup is outside. So you have 100%. That means all the sample, the in-groups monophyletic with respect to the outgroup here, Kula and Eritrea. But within the in-group, kita ada 2 apparent states ataupun dipanggil haplogroup which is this one. Batang air Mudu is the eastern part of Sarawak. This is the western part. Okay, you nampak 2 states here. Okay, so you kena copy, image copy, masuk dalam Word. Dia akan keluar. Okay, so this is you punya NJ3. Okay, now NJ3 only produce 1 tree. You nampak sini dia tak ada apa-apa, tak banyak trees, only 1 tree because they go straight to the distance. Okay, and sama juga dengan yang ini. So you go to phylogeny, you go the parsimony. Okay, the parsimony tree. Construct parsimony here. Yes. Sama juga. Now, parsimony dia akan keluar banyak trees because parsimony is look at the shortest mutational event. Okay, and we give you many tree. Regardless of how you arrange the punya taxa tu, the clade tu, we give you maybe 100 trees that show the most parsimonious tree. So which tree are you going to choose is, that's why you have to use a consensus tree. Only parsimony or Bayesian use because they will give you a very banyak tree that you need to do the consensus. Consensus is the tree common to all. Okay, but livelihood and Nabichani, they will not give you consensus. They will give you only 1 tree. They produce only 1 tree. Itu you kena faham. So when we review the journals or any of the MP, we look at this kind of situation. If you letak situ dan figure out consensus tree of neighbor journey, then you tahu you tak faham apa benda you belajar. Consensus tree only for those yang bagi you banyak trees. Parsimony and also Bayesian because they the probability, so they give you many trees that have the shortest length atau dia bagi the most parsimonious tree. then you have to do the consensus. Tapi kalau the neighbor joining distant method, like the hood also distant, they will give you only one tree. So you have a maximum likelihood tree. Tidak ada consensus di situ. Okay. So you nampak sampai dia sikit lagi ya. So you can see masa saya when you get to have so many trees for this particular analysis. Jadi sikit lagi tambah kita akan, saya dah cakap kita akan start at 11:15 today. Okay, finish. So dia akan keluar. So this is a parsimony tree. So you look, dia punya ni memang nampak. Okay, this is only one tree. Tengok sini ya. Macam mana saya tengok sini ya. Where do I get to see dia punya tree yang banyak tu. Okay, tadi dia tak nampak this icon. Now you nampak how many trees yang ada. Nampak sini ya. Sekejap saya pergi sini. How do I tak boleh ni. Nampak tak kelas? So di sini ada one of 8 tree. Jadi ada 8 trees yang parsimonious. That's why you need a consensus tree here. Okay. So when you have a consensus tree, you have to root the tree. Rooting adalah yang ini ya. Ini this is the icon rooting. Rooting maksudnya you go to the out group, you kena root. This is you punya out group. So this will be your consensus tree. Yes, the consensus tree. Actually sama dengan this distance tadi, neighbor joining. Okay, you have two plate here. And this is you punya, walaupun value dia kurang, but still high support for the whole is the in group is monophyletic with respect to the out group here, and they have two plate here, two apparent plate. Batang the western part and the eastern part of Sarawak. So itu maksud dia, okay. Consensus tree. Now, then we do layout tree ni saya buat. Layout tree is very tedious. Kita tak buat lama. Let's say kita buat dua saja, okay. Sebab dia kita buat dua iteration. Although this is not ni lah. Dua is sebab I just want to have a very quick, okay. You can nampak dia. Let's say kita buat dua iteration, dua kali sajalah. And make sure you punya distance model is sama. So you can see there's only one tree. Tak ada icon on the number of trees. That's why saya kata neighbor joining neighborhood only give you one tree. And you can see here, actually walaupun two iteration they already give you the same topology with the neighbor joining and parsimony. So when all of your analysis give you the same topology of tree, topology maksudnya the relationship is the same. Both all trees give you two haplogroups for this particular species, then you have a very strong findings, okay, to be explained and etc. Okay. So I think kita finish dah ini. I just go back to kita punya slide. Hold on. Okay. So this is kita tadi. You can look at the chemorapidity, okay, parsimony. How you, so all the slides they already give you how you copy. Okay. Cuma saya tak tukar lagi dia punya this is mega 4, okay. Mega 10 tadi yang saya ajar is mega 10, but the process is similar, okay. Cuma the updated mega that is being used, okay, for the hands on, and this is the one that in the lecture notes is for mega 4. So you can see this is how you just copy the image and you put in the word, okay. Sama juga, okay. So how do you so this is the interpretation in your manuscript. So ada dia punya thesis ataupun learner is you identify whether your sequence is a good marker by looking at the variables and parsimony sites and the segregating sets, and you look for the sequence analysis, okay. Sequence divergence, your distance within groups and between groups, and whether your distance actually is within in the domain itself, which is they are still not less than the distance between the groups. Okay, kalau you punya sample to lebih di outgroup, that means something wrong with your sample, you have to redo. And your follow relationship using the neighbor joining tadi, make maximum likelihood dan juga maximum parsimony. Remember, likelihood and neighbor joining give only one tree. The parsimony analysis, you have to do the consensus tree because dia akan bagi banyak tree with the most parsimonies, and you have to do a consensus tree. Okay. Then you interpret the result. Okay, ada soalan? Kita dah habis. Okay. Kalau tak ada soalan, kita finish lah for the analysis. Nah, this is just to introduce you what are the software being used. Kalau you masih tak faham, it's still okay. Once you get your data nanti, once you do PCR, you can isolate the data. And then you do the purification, you send for sequencing. Nanti atasnya ada demo how to send the sequencing. Once you get your sequence, then you extract another sample for the gene bank so that you boleh dapat banyak data for you to do the analysis. So when you do the part analysis for your mini project, then if you have any problem, if you tak faham, then we can have a slot session, a separate session, hands-on in the computer lab. Okay, saya rasa by the time Nisa pun dah balik cuti, so you should be okay lah. Kita akan cuba download in the software dalam komputer untuk all the software being used, and you can buat di situ. Okay, any question? Kalau tak ada, so I will see you in the lab after this. Kita start pukul 11.10 lah, saya dah beritahu dekat lab system.